Okay, and now let's begin our presentation. Our project is a wireless big data transceiver for IEEE 802.11 network. First of all, it's about our induction. As we know, at the low transmission rate with media access control and the physical layer control restrict to support high data rate application. So current WLAN systems have difficulties with new higher data rate services, such as high definition, data vision, file transfer, and online gaming, video teleconferencing, lecture. So in order to enhance the throughput of the wireline systems, we already have one method which is in MAC layer called frame aggregation. It's a time. It reduces the timing and headers overhead by aggregating multiple frames into a single large frame and then transmit in a single channel access like this structure. And we could see that in one frame, and there are aggregated multiple frames. Subframe, and each frame has its own header, which already been reduced by the system. But we can see that although it contaminated some subframes, but it all still has some headers, and so the headers are not completely deleted. So to further enhance the throughput and improve the efficiency, we propose a new enhancement method in the physical layer, which we can enlarge the frame directly by changing the mechanism of the information transmission recovery. We can see from the structure that we can directly enlarge the data in the structure and no longer need to contaminate these subframes. So in this case, we didn't have any redundancy like headers and overheads. So in this case, we can have a greater data application throughput. So to conclude, we aim to construct a system that can deliver large data packets to achieve the greater application data throughput and substantially improve reliability under our lab near air-free environment. And last time we have built the single-in and single-out OFDM systems based on the lab view. So next we need to focus on the 802.11a standard, which is based to modify the mechanism of the information transmission and recovery. We could see that based on the 802.11 standard, we have the 10 identical short sequence, 10 identical symbols in short sequences, and 2 identical symbols in the long sequence, and followed by the signal and the data. And plus, we also have the pilot signals inserted into the OFDM subcarriers in each block to make the coherent detection robust against the frequency offset and the phase noise. So, in order to modify these mechanisms, first of all, we need to know about our system environment. Actually, in our system, our environment in our lab is nearly error-free, which means there is almost no obstacles between our transmission and the receiver. So it is a slow fading channel in our case. And plus, we can focus on our channel estimation methods. Channel estimation methods depart two kinds of methods. First of all is bind method, which needs a statistical of the received signals, and which need the accurate the channel length or some other information which will require a large amount of computation. So in our case, it's not practical. So we focus on the second method, which is a non-bind channel estimation method, which utilizes the pilot symbols or training sequences to obtain the channel state information. So, then we focus on the concrete pilot symbols or the training sequences. First of all, it's about the pilot symbols. We know the pilot symbols are inserted into the subcarriers of each block of the UFDM symbol. So it is to trap the fast varying channel, which we call the reduction of the transmission rate, because it account large in one symbol. So when we transmit a very large packet, it may cause the reduction of the transmission rate. So as we know, our system environment nearly error-free, slow fading. So in this case, we no longer need the pilot symbols. So we drop the pilot symbols in the standard. Then we focus on the training sequences. We know the training sequences combine short training sequences and the long training sequences, which if we want to enlarge our packet size, we choose to insert it linearly into data packet every certain interval to estimate the respective channel. As the short training sequences are used for course time, and the long sequences for fine time synchronization. So in our slow feeding channel, we only use the short training sequences to estimate our channel. It is already sufficient because of our slow feeding channel. So to conclude, to reduce the time complexity and enlarge the data payload, we choose only insert short training sequences into data packets every certain interval, which would be already enough to estimate the respective channel under a slow fading environment. So, plus we need to consider about our channel estimator. We consider two console estimator here. One is LS estimator, which are calculated with very low complexity but suffer from a high mean square error. Another one is MMSE estimator, which perform much better than LS estimators, especially under low SNR scenarios, but with a relatively high complexity. Anyway, in our case, we choose MMSE estimator because it performs better, and our system anyway has some noise, and we want more accurate result. Besides, the estimators utilize the consequently inserted sorting sequences to perform channel estimation for the translated data symbols to regard the transmitted symbol. Another part is about synchronization, which first of all is about the symbol timing. The symbol timing, we use auto calculation to do initial course time synchronization. We only perform the symbol timing once for the first routing symbols to detect a packet arrival. Because once we detect a packet arrival, the whole packet we already detected right. So we only performed it once. It's sufficient. Another one is about the frame synchronization and the frequency offset correction. In this case, we use the schematic and coarse algorithms. We perform the frame synchronization once to detect the start of the frame, similarly like the symbol timing. And differently, we perform the frequency offset correction for each inserted short sequences to estimate the frequency offset of the corresponding symbols. To estimate it more accurately for large data packet. So, finally, we do the simulation here, and we found that in this case, we use a noise equals to -10 dB. And under these cases, we found that with more numbers of certain frequencies, we have less the average bit error rate here. So we found that in our simulator, inserting more short training sequences, we can have better performance of the information recovery. So we applied it to the real experience by USRP. We found that in our real system, by inserting more short training sequences, we can achieve the maximum packet length more and more, and finally we can achieve about transmit twice the packet length than the original. If we add the 6 short sequences, we will find that the maximum packet length will not increase anymore, because there should be a trade-off between the throughput and the delay. We cannot just always inserting the short training sequences. So, to make conclusion, our system already accomplished to enlarge the packet by inserting short training sequence linearly into the OFDM symbols in the physical layer. Our system has advantages compared to the frame aggression, like we have no redundant overhead, and as we cut the pilot symbols and the long training sequences, so we have larger payload and lower delay. So these are our system advantages. But our systems would only be practical under slow fading environments, as we only add the short training sequences linearly into our symbols. We discard the pilot symbols and the long training symbols, so our system only be practical under the slow fading environment. So to further enlarge the data packet size in the future, we can explore the design of the training symbols more, like we can use shorter training symbols instead of short training sequences. We can invent a new kind of short training sequences, which is much shorter than the STS, to produce channel estimation. In this case, we can enlarge our payload more, and the delay will be less, and the overhead would be less. So in this case, we can achieve more channel efficiency and data throughput. So that's all about our project. Thank you.